Merci beaucoup. Thanks a lot, Professor Gerard, and all important person, Carol and other, which we have contact, and I am happy. I am here third or fourth time. I don't remember. So it's nice to be again. So my talk is related with combinatorics and with some physics, because Fock space is at least that name. Coxeter groups. This is the main Coxeter group. What I speak here is only permutation group or sign permutation group. That means hyperoctahedral group. That means permutation which has, when you look for the matrices, is like plus minus one in each row and columns. And yeah, type B is the next series of groups, Y group or Coxeter group more generally, starting with permutation group, which is the type A. Yeah? This is type B. And type B and C, when you look for Lie groups, is a little bit changed, but here for groups not, for Y groups not. And Coxeter, and this should be probably written Coxeter-Dynkin groups, but Dynkin mainly look for Lie algebras. So, but this is very, very close business. Yeah. So, yeah. Okay. So, as I wrote in abstract, our talk, we use infinite hyperoctahedral group. I will be explaining more. And we found two parameter deformation with Q plus Q minus 1, which is positive definite. And this is important for us, positive definiteness, because this is related with symmetrizators. Usually, you know, symmetric Fock space, anti-symmetric Fock space. This is related to trivial symmetrizator or anti-symmetrizators. But here we use more parameters, and this is, but here yet still is more interesting things. And we constructed new type of Fock space, which we call cyclic Fock space. We did for the series F only for permutation group with my colleague Madeleine Gucia. Now we work with my collaborator, my student Maciej Dołęga, Victor Eismont, Światłosław Gal. More, and that paper is just appeared this year in Journal Functional Analysis. Rather big paper, so also with, yeah. And then all details you can find there, of course. Yeah. So main object, main machinery will be positive definiteness of the function on the group. So if you have any group, yeah, we look for this function which is positive definite. That means that kernel G minus 1 Gi is positive, yeah, as a kernel or function. This is connected, of course, with the famous Bochner theorem that on the real line, when you have probability measure and you have Fourier Stieltjes transform, the Fourier that transform is positive definite even only if the measure is probability with some normalization. So that starts. But positive definite later was extended by Gelfand and his school, Godemain also in France. I like his paper in Transaction 52 or 54. I like this title is positive definite, maybe in French. Excellent. That because this is related to the representation theory of groups, unitary, of course, representation, and a lot of is done in this direction. Because this is generalization of Bochner. So we will do in this business in that direction. So, but starting point was when we come to the group, of course, it was Poisson which observed that function q to the length, to the modulus of length, is positive definite. So this was Poisson, that function for q to the length function, n is the Fourier transform of nt demi t. Maybe minus should be here, from minus pi to pi. This is the famous Mies probability measure. That measure is well known. This is Poisson kernel depending on q. Usually q is here between 1 and minus 1. And that kernel you can calculate explicitly. And that was the first important result by Poisson. Usually people just call Poisson kernel, yeah, this one. So this is Fourier transform, that function, yeah. And that result was extending 79 by Hagerup, Uwe Hagerup. Maybe I should dedicate these talks to his memory. He was our excellent mathematician. Unfortunately, he's not among us. And he started to prove such a result for free group. For free group, Fn, free group, which is just, so this is like for n in Z. This is Poisson. But the question was, what is the free product of Z? You know? This is the, like this. This is free group on two generators, free group. And that usually we wrote like this, yeah. This is such a beautiful tree. Free group generated by two generators, let's say x1, x2. So here is x1, this is x2, x minus 1, and x, la. So this is homogeneous tree, like for one generator, this is classical tree, 0, 1, minus 1. This is generator x1, x minus 1, and so on. So this is one generator, this is two and more. This is usually a very nice tree, and that was Uwe Hagerup obtained first positive result, because maybe if you are a mathematician, you know where that free group is usually was used to counterexample. Free group was, but no, he in 79 proved positive result that such a function, q to the length, when length function on the tree, on that group is just path. So you have here, if you would like that element, you should calculate 1, 2, 3 to 0. So distance, L on free group, on G is just distance G to identity. So this is identity. This is the usually people call this Kelly graph. And that was the first. Later on was problem how to. Of course, these groups and that object is isomorphic. So this is isomorphic to free product of two elements group. Free product of two elements group. You don't distinguish x1, this was x2, x3, x4. And that was question, how is this for other free product, or even more general for Y groups? So such a question also was posed by, I think, by many people, if maybe Coxeter, because that result implies that the result that function is positive definite implies that free group is not Kazhdan group. Kazhdan group is called nowadays property T. Yeah, but this was discovered by Kazhdan, I think connected with Gelfand or something, but this was Kazhdan property. That means the trivial representation in dual object is isolated. So it's very, very strange result. Yeah, because this is no torsion, but dual object can be or have torsion anyway. So, and property T or Kazhdan property is very restricted, has a lot of application also to physics, mathematical physics, topology, algebraic geometry, and so on. But then we prove with Januszkiewicz, my colleague in Wrocław, and Spazier, many years ago, you see, I was just young boy almost, that function q to the length is for all Coxeter group. And Coxeter group, this is nothing else like group generated by orthogonal Coxeter, or some people call Weil, Hermann Weil groups, WS. That means that S is set of orthogonal reflection in some Euclidean space Rn, and W is the group generated by that set of. So it's very simple case. Of course, the simplest example I always teach everybody is permutation group. Yeah, when you take generated, but P1 is just reflection 1, 2, P2 is reflection 2, 3, and so on, P3, and so on. Of course, the simplest way is just take symmetry of the tree. So this 1, 2 is that reflection, orthogonal, and 2, 3 is that reflection. Yeah. So that by 2, and so on. This is S3, S4, and so on is more. So this is that. And even for that group, if you have length function here on Sn is just, for sigma is just minimum of generators k, when sigma is written as a P1, Pk, this you can read really as a number of inversion. So a number of ij, that I is less than j, but sigma change the order. This is a very important function. This is called inversion number, inversion. When you look for the book of Knut, Arts of Programming, there are 3 volumes. 2 volumes are just very technical, but third volume is just about that group and that function, because this is sorting. This is very important in library, in life. You know that you should have sorting, and what we proved that function q to the length function, and I was surprising that we proved this ATA, yeah, sigma from Sn for q between 1 and -1. Of course, when q is equal 1, this is symmetrizator. Yeah? Q, this we call PQ, Pn1. This is symmetrizator, summation over O permutation. And P -1, this is anti-symmetrizators. -1 to the length function of sigma. Important is 0. This is constant function identity, and so on. But that between also, and of course this is something what we usually wrote as in the parameter q. Here is 1, -1. This is a q. This is 0. So this is called Bose-Fock space for Fermi, and this is the called Maxwell. Voiculescu, some people say, because Voiculescu repeat this Maxwell, of course, this is not any symmetrization. Yeah. Okay, and this is how we form this. Just we take full Fock space, we take as a real Hilbert space like Rn, real Hilbert space. You can take, n can be infinity, of course, mathematician like every dimension, and you take full Fock space, so Fh with 0, this is the vacuum, plus h squared, and so on. So tensor without any symmetry. Yeah. And then to obtain Fermi or Bose or Q, we take tensor Cn, eta n with Q, and we paid PQ n symmetrizator Cn eta n at 0 when Cn and eta n belongs to tensors of the length n. So this is the ideology what we teach in Berezin book, Second Quantization. But of course now what is new, that Q can be between. And for example, the famous physicist Greenberg, he conjectured that not exists Q equal 1, not such ideal Bose-Fock space. He would like that Q, the most important Greenberg, conjectured that Q should be almost 1. So like 0, 0. He said that this is Bose because you can calculate something. At 1, so this was philosophy, and even he make experiment for particle physicists. Bose statistic not exist. Of course, this is connected with Bose, Einstein, and other, and the what we call Q canonical commutation relation. Of course, this is not my talk, but almost anyway. So, but I should start. AF A daga G minus Q. We discovered this, rediscovered some sense in 90s, identity, Q relation. Everybody, of course, among physicists say, Marek, what you are doing, everything is no. Is no for Q equal 1, minus 1 and 0. But for Q 1/2, you should have realization. That means that creation operator, of course, G on Xi should be one-sided shift. This is clear, but annihilation vector should be such that this is the dual of creation, some sense conjugation. And that is the problem, because if you have dual, you should have Hilbert space, no arbitrary. Of course you can do, but this is no mathematics. This is maybe some related to maybe Einstein relativity theory. Anyway, but here, that result that we have Q to the length, because that PQ, as I wrote, maybe I don't wrote here, PQ n is just summation Q to the number of crossing or length function on that group, permutation group, sigma, what we call Q symmetrizator. Even this is not projection. This is not projection. This is one of more difficulties. But nevertheless, this operator is, we prove, that we prove with Speicher. As I said, there is Schwarz, my student, and other colleagues. So we extended that result later. So, and of course, if you wrote such a relation, most of people ask, oh my God, we know this. But usually physicists put Q and we say this is okay. No, you should use mathematics. You should know that the function Q to the length is positive definite. That we have scalar product and is okay. Next step will be put Q modulus 1. This is related with anionic commutation or particles, anionic commutation relation, but it's more difficult. I will not speak today, but we have a series of papers with Litvinon and Professor Wierszyk and so other about that anionic business. But this is not the topic of, this is related everything to permutation group. So particle, very special statistic. But now we would like come to the more delicate, I don't know what is the particle, maybe you are physicists, so you should know this, what is this? So what is interesting, that function, unfortunately, are not central functions, so it's not constant on conjugation classes. Of course, the Q0 and minus Q1 and minus 1 is okay, but this is not. So we couldn't use. So we with Guta we extended to the to that case when that function should be invariant. It's much easier because you are coming to commutative some sense analysis. Yeah, but this not. Okay. Yeah. So this was connected with the Coxeter Y group, generated per reflection, but S was number, what we call primitive reflection. So this is like in Dynkin Coxeter diagram. We use only reflection on permutation group. We use that business, yeah. That is the P1, P2, and Pn minus 1. This is that. But this is not enough for us. We should use O reflection. So O reflection. So this is only we'll call primitive reflection or simple. This is connected with the Lie group. This connected with the root system, of course, because all reflection are just reflection with respect to hyperplane orthogonal to root system. If you take only sim roots, we have obtained primitive, and that is business. But we would like all roots, or this equivalently all reflection. On permutation group or on O reflection on Y group, Y group WS, and that reflection we call num T, and T is nothing else like conjugation G S G2 minus 1 when G belongs to the W. So O reflection. So in case of permutation group, this is just set of O reflection, maybe we call Pij, yeah, which change. So this is usually we call it as a mathematician Ij, yeah, when I is let's say less than J, less than N. So this is that, and that function is also interesting. That function when you take length function with respect to this, and Q to the length function with respect to O reflection on sigma on permutation group, yeah, is positive definite, and this is important, not for OQ. This is just quantization. This is only if and only if, that is easy to prove, when Q is plus minus 1 over n. When Fn, of course, is infinity, 1, 2, 3, infinity means Q is 0. So this is quantization effect. Of course, plus minus 1 is Bose-Fermi. But what is the, when you use Q1/2, this is you obtain another statistic, another commutation relation, and we did this very well with the Guta. Yeah. And I have no time to speak about this because my talk is now coming to reflection of type B, so group which is hyperoctahedral. Yeah? So maybe now we come to that group, and if you're not yet familiar, I recommend you, of course, Bourbaki, Lie groups and Lie algebra, chapter 5, 6, 7, or 4, 5, 6. This is excellent. When the introduction was by Jacques Tietz, and this is excellent. Of course, it's Russian. I study Russian because in Poland we have Russian translation, of course. Yeah. Okay. I would say that this is some historical, that function are, when you use O reflection, they are just central, so invariant under conjugation. So much simpler. And beautiful result was obtained by Elmar Thoma. This is mathematician from Munich. He was my teacher, so I know this. And he found O positive definite function on group S infinity. So, and this excellent, I have no time to speak of it, but this is beautiful result. And the result is very, very deep, and a lot of, like Wojkulescu, Wierszy, Kerov give another business about this, and this was center of harmonic analysis in 80s, 90s. And also Wojkulescu, this was coming to the random matrix, and that to the free probability. I have no time to speak about it, but you can imagine that this is, yeah. So what is motivation? Maybe I said motivation. So motivation, in case permutation, length is just what I wrote here. It's just, but this, my teacher in Latin say repetitium mater studiorum est. So repeat. So with O transposition, O reflection, minimum number of transposition, but that function is n for permutation Sn, n minus number of cycles. And everybody from you using number of cycles. Cycle is everywhere because every permutation you decompose of commuting cycles, and that is beautiful mathematics, yeah. But this is just that you use O transposition, and that what I said here, that the simplest example of positive definite function is just Q to the, when Q is just what I wrote here, plus minus. And we use that function to construct Gaussian operator and Fock space, and which now will be extended to case of hyperoctahedral group, or that, in other words, group which is the semi-direct product permutation of, and that group is the symmetry group. Permutation group is symmetry of the simplex, triangle, and so on, but hyperoctahedral group is symmetry group n-dimensional cube. This is related to quaternionic business. And that group, Bn group, will be really Y group of SUN, but under quaternionic. So I know that a lot of people study quaternionic business, but not so much, yeah, still. But I think our result will be, in some sense, show you that this beautiful mathematics, maybe use many physicists. I hope here to follow this. Of course, I make propaganda, but yeah. So what is Coxeter B or Y group, which we call hyperoctahedral group? This is a group of permutation on the set 1n and -1, -2, -n. This is connected. That group is, this is symmetric group of the cube. So sigma n, or I call Bn, or sigma n on Bn is the symmetry group. This symmetry group of n cube, n-dimensional cube. Yeah. So, for example, when you take the simplest cube two-dimensional, usually 1, -1, or this is 1, 2, -2. Yeah. This is better. And that symmetry is just what is exactly. This is such a permutation that sigma belongs to that group Bn, even only if sigma minus k is equal to minus sigma k. For this is sigma k involution. K is 1, 2. And so here is, you know, the simplest description of permutation group. So 1, 2. So this is 1 minus 2. This is that symmetry. And that between 2 and 1 is that symmetry. This is commutative. But of course you have 1 and 2. So you have like this, yeah. Okay. So this group is usually is written like this. We call P0, P1. You know? So this is the 1, 2, but this P0 change 1 to -1. You know? Yeah, okay. So this is that group, and usually people call like this means 4. So P0, P1 to power 4 is equal identity. In the case of permutation, you have bread relation. Okay, so this is what I said. That group is equivalent symmetric n-dimensional hypercube. This is O permutation on the set which satisfy that condition. And that group is, as I said, Y group of type B, and this is Y group of unitary group over quaternions, or maybe special orthogonal group with special business. Okay. This is some example. Maybe this is for they have a lecture for some students, so, but you probably can imagine what is this. And what is new? I say new things in that machinery is that we have, of course, cycles, because that group, hyperoctahedral group, is also permutation group, but have additional structure, that involution. And that implies that we have two types of cycles. This, by the way, was discovered by Carter, but not the famous, was just here, the other Carter in the 50s. That we have two cycles, because if you have cycles in the negative business, yeah, so you have cycle, let's say 1 comes to 2, comes to maybe 1, this is cycles, okay, and then come back, yeah. But you can also comes 1, 2, to -1. And then comes, I don't know, comes again and comes to 1. So this is we call positive cycles, and this is called negative cycles. So that means, of course, if you come to -1, because if you come to 2, from -1 you come to -2, you can check it, and so on, and you come to 1. But what's happening? Positive means that in your world of psych, not negative. And usually we wrote this on pictures. So 1, 2, 3, -1, -2, -3. Yeah. And usually cyclics are like here, 2, 2, tralalala, and here is just reflection. This is, but this is positive. But negative, if you come from here, let's say to this, to 2, no, anyway, to 2 and then to minus, maybe this was not to 2 and then to -1. So we just come through the, merci beaucoup. So I speak too much, but as my teacher say, or Pythagoras say, langsam, aber sicher no. Festina lente, Pythagoras said. I don't know, don't remember. Okay, so we have 2 types of the cycles, and so we have much better structure, and that function, of course, are also central functions. So that is invariant under conjugation. Yeah. You are happy that they are a central function, I hope. Everybody, I also. Good. And there are, I wrote formally what means there are 2 parts of the cycles. One cycle comes only positive and negative, and other comes mixing. So this is positive and negative cycles. And of course from this you can ask of the deformation coming from that business. And of course will be interesting what means from physics. Because you now take like symmetrizator, anti-symmetrizators, yeah, to the positive and negative cycle. Anyway, this is everything is written. I will not come to details. This is written in our paper. So example, you can follow. And so the conjugation class of that group, with the pair of partition of numbers, sigma 1, sigma k, when at most total size most n, when first partition has no parts of equal 1. Yeah. So this is connected with the positive, and negative can be negative. The simplest negative is 1 comes to -1. Yeah. So it's like the negative. This comes 1 to -1, and then -1 is to 1 by definition. So this is the trivial, some sense, but most important. Yeah. Good. Oh, thank you, Gerard. I just, okay, I be now comes to further. So this is example. You can follow positive reflection and negative reflection. I hope that I something, no, okay. And of course now we will be distinguish number of positive reflection and number of negative reflection in the some words sigma. When we wrote that words, of course, here is important that there will be not, this we call no mixing. So means that not in the minimal, we have not repetition. Yeah, so this is trivial. And we in paper we wrote, because most people don't distinguish this. This we distinguish, and we wrote mathematical paper that was false papers. Anyway, I don't say who about. So we have 2 function, 2 parameter function on just q to the positive reflection, and q plus and q minus to negative reflection. This is, and of course now is question, when is this coefficient of unitary representation, and when is positive definite? And this is main result. Of course, this is written what is some exam, tralalala. And now, of course, we come to infinity. If you have something to do, as people know, mathematics and physics, you can see at infinity. At finite state, you can see nothing. You know, this is, you have statistics, so you have a lot of business. And now we come to the positive definite, with this positive definite and central means that constant is called character. This is definition by Professor Thoma. But among the characters are important extremal. extremal point among the set of normalized, I mean identity is one, and that we call Thoma characters. Some people, Professor Thoma wrote 2 or 3 papers when of course he interested it, and if you like representation theory of von Neumann algebra, this is connected with factor representation, factorial representation. So anyway, okay, but I have no time. And now I come to you with our main theorem from this year. It was published, but of course, during the COVID time we work. So this was for our COVID very excellent because we can stay at home using computers and prove that theorem. So theorem is like this. We have a 2-parameter function, Q plus 2 positive reflection numbers and negative. And the result is, if you take any numbers, natural, m and n, which sum is not 0, and epsilon is, so we have discrete series, so like was in permutation group. So you could plus minus, this is like fermion boson. Of course, this is that, and this is that excellent, that should be, this is discrete series, and we have also for Q plus, we have continuous series. So this is something appears what for, usually in Lie group is natural. We have discrete series and continuous series. This is, but here is the, and of course, I think the chairman is saying that is, okay, I have a lot of things, how we proved, la, and the main thing is the cyclic Fock set, what we are doing. So now we work with this separable real Hilbert space, which now we make double case. And on that tensors, of course, we have trivial tensor scalar product, but we have natural action of our group, our group hyperoctahedral group, because we can identify vectors here as a sequence of tensor x1, xn, and negative x minus 1, x minus n, and we act like groups act. So this is not nothing important, and then we have direct, this is full Fock space without any deformation, and we have now made deformation using that character what we discovered, positivity, and positivity gives that we have now, if we have completion, this is the Hilbert space, the full space with 2 parameters, and we have creation operator natural way, acts left and side, and adjoint is annihilation, and of course, as a physicist, you know that important are commutation relations. So we have commutation relation, very special, and here I will not come into details, but you expected that if you have the 2 creation, creation annihilation, probably I should. Oh, here. You have creation annihilation operators, so we have commutation relation. If here appears Q plus, Q minus. Q minus appears just like in this was in the series A, but we have real second quantization operator, Q gamma, Q plus. So this is mixed. I don't know, I never found in literature that is should 2 types of quantization, and we obtain, this is calculation. But now, of course, for us, I'm coming from now harmonic analysis and probability, so for us it's important, of course, this is some, because the conference about combinatorics, so we would like to have weak result, Wick theorem, the normal order, how to calculate normal order. For this we need some nice combinatorics, because this conference, so this is combinatorics. I don't explain, but you can imagine what is this. You can ask, or we can look for paper. So yeah, so I don't come, but it's important here that we have such a natural pictures, but this means that this projection from O to pairing to non-crossing pairing. Yeah. So that low down is the no crossing, but this is crossing. Yeah. And that is the important we discovered with Guta on the permutation, but this is more general for negative and positive. Oh, so I like this. Of course, to explain this is more time, but Professor said me that I should finish. But for us, it's important Gauss, this migration plus annihilation. This we will call Gauss operator. And now we, of course, we have weak formula, the normal order, and up here Q minus to negative, and Q plus to C minus number of cycles, like you expected. This is a result which is just mathematics, but maybe some physics interpretation. But now comes to mathematics, and this is the Schrödinger important of mathematical differential Weber equation. This is that Schrödinger equation. This was done much before Schrödinger, 100 years maybe, Weber. Differential equation with parameter C. And that, of course, this was rediscovered by I.K. Wimp and Kerov, student of Wierzyk. Solution explicitly written. And what is that DC? This is D0, the derivation, but that maybe we don't, the density is difficult to write, but orthogonal polynomials, like for Gauss is Hermite. Here is generalization Hermite, only with parameter C. So Hermite is when C equals 0, but we have C which is not 0. C can be bigger than -1, and that is what we call ASCII, and that maybe I should finish slowly. So for Q positive, we obtain ASCII Kerov distribution, semicircle for Q, and for Q plus negative, we obtain discrete measure like in some generalization of fermionic. Okay, and then we have moments when special case when Q plus is just Catalan numbers. Professor Penson will be happy. Catalan numbers you also like, yeah, with some, and that is connected with the Wigner semicircle with the random matrix with free probability. Yeah, so okay, this is references. So this is my paper with my collaborators, but not only, because the most important, of course, is paper by Wojkulescu, Hagerup, as you see, Carter, especially Carter paper 72 about conjugation classes in the Y group. So I think my time is over. I hope that I don't give everything, but I'm happy that I give you some. And you should remember also that in that case of that group, there are two types of cycles. And now, as a physicist or mathematician, please give me what that means. This is some like special Fermi, Bose, or what is this? I don't know. Thank you once more for invitation and for your.
So we have short time for short questions, but thank you so much for your talk.
Thank you very much.
Yes, Gleb.
So you can consider folding of your Coxeter group with if you consider A to N. So if you consider Y group of S to N,
yeah,
and then you consider symmetric permutations,
yeah,
then you get just folding of your, and so therefore if you just have characters from this symmetric and just for this folding, so how are they related to?
Yeah, no, so this is the symmetric, anti-symmetric, this is the characters, only central and zero, also identity, zero identity, this is correspond to regular, but here is more larger class, because we have, because you have two parameters, so you have really pictures like this, that we have, when you have only one parameter, we have plus minus 1, but this is 1q, but now we have second parameter also, so we have our reparameter this is second parameter q2, and also important that what I say, plus minus 1, and this is 1. So this is 4 characters also, and it's special symmetrization. Yeah, and that is. But this is your question, or so maybe I don't know. I mean, maybe in the break I ask you more. So anyway, so this is just, but of course, all beautiful word is here, probably. But thank you.
I didn't understand where the link with the Wigner cycles comes from?
With Wigner? No, with connection with Wigner measure. Measure. So that is because this of course I don't give explicitly formula, but that in the Hermite polynomials, because this is easy to say, n plus c h n. This is that one, the orthogonal polynomial. When C0 is just Hermite. But of course here is some reparametrization, and Wigner measure corresponding to the case, let's say xn Wigner polynomials. This is Chebyshev polynomial of the second degree plus, so no n. And that is very special. This is that case. This is, in some sense, not interesting from physics, but mathematics is very, and that. So what we are doing really, like in mathematics, what I always say that every business comes from first you should have free object, and then make deformation. So we have here, we have free object is the free. This is the trivial case, and then you make deformation, for example, this. Of course, we have 2 or 3 papers in our, which we have deformation using not O transposition, but only that simple roots. So, and that is another, probably Professor Penson will be interesting, because this is related to another kind of Meixner-Polacek. So this is related to different kind. I have no time, but Meixner, Polacek. Check polynomials and measure. One of the important is there are 2 parameters also, I don't count, but one is important, this cosinus hyperbolicum x, this is measure to maybe square. And important is that measure, Fourier transform is the same. This is like Gauss, but cosinus. And that corresponding to special deformation of that group, but using only simple roots. I have no time. This is a series of papers that I wrote some years ago, but in my, you can see this, everything is, maybe before is written, some Litvinov, no, with some other, my Victor, anyway, with some my students, Eismont and Hasebe from Sapporo, we work on this, and the Meixner Polacek. We are very surprising that using deformation different kind, you obtain different statistics. Yeah, and I have no time to speak about this, but you can believe me. And thank you for your question. And so Wigner is important for us, but as a random matrix. So of course here is the question. How is random matrix around this?
Yes, that was my behind question. Sorry, I was confused, but
where is random matrix?
On the smartphone.
You know, that group is some sense like a random matrix, because permutation group you can look look as a matrices. The permutation makes 1, 0, 1, 0, and so on. So matrices which only have ones, but that's Bn series, Bn is plus minus. So, and that should be also, I know paper by Professor Philip Bian about connection, random matrix permutation with the Wigner. But also here should be, one of my students work on this, and I should be soon some. So this is only small change, but very, very, I think my time is over. Thank you. And we can discuss, I am 3 days, so.
I am sorry, but the art of the chairman is à la recherche du temps perdu. So.
Thank you very much.
Thank you very much.
Thank you very much, yeah.